Right, it's 8:30. Let's go and get started. Good morning, everyone. How's everyone doing today? Good. Yeah. Good. Okay, so this week we have just kind of a shortened week, just because we have our midterm exam on Thursday. So you should have all the material that I posted out for the midterm exam. So homework 6 solutions I put up yesterday. The review video I actually recorded and uploaded on Friday, but I just forgot to announce it until yesterday. So hopefully all that is useful. I have one more office hours until before the exam, so that's tomorrow from 1 to 2 p.m. And so if you have any last minute questions while you're studying, definitely feel free to come by. But if you can't make it to office hours, you can always email me as well. We either set up another kind of appointment outside of office hours that works with your schedule, or we can correspond over email. That's fine. Okay. But yeah, don't be afraid to ask questions, because I know there's kind of a lot of content to cover. I know when I was recording the review video, I had a hard time kind of getting all of it within that hour. So I know there's still a lot out there to cover. So please reach out if you have questions. I'm always here to. Okay, so today the plan is we're going to continue on with our discussion of probability and statistics. So we're still kind of in that early phase of kind of introducing a new topic, and so we're mostly going over mostly conceptual stuff. I think probably the stuff we're going to cover today is fairly new. We're kind of moving beyond kind of the mean, median, and mode stuff we did last time. So now we're talking about random variables, and today we're going to get into confidence intervals. Okay. So these are kind of the more useful kind of tools, or more useful kind of concepts to probability statistics that are kind of more relevant to your lab classes and just kind of this uncertainty in engineering. All right, so I think that's all my announcements. Are there any questions I can answer before we get started? Okay. All right, so let's go and get started. And so the theme for today is random variables. And probability density. Okay. So last class, we introduced this concept of a random variable. So a random variable, the idea behind a random variable is that there's some uncertainty associated, right? So you don't know its value for certain. So the idea with the random variable is that every time you measure it, every time you observe it, it's always going to have a different value. So measurement, when I say measurement, I mean every time that we actually put at the random or record a value for that random. So the example that I kind of keep bringing up is the commute time, right? And so if you measure, if you measure the amount of time it takes you to go from home to campus, it's going to be slightly different. But there are a lot of uncertain factors, and a lot of kind of random factors that are out there in the world that prevent you from this being exactly the same thing. Traffic, things like traffic lights, pedestrians, maybe your car's having issues, stuff like your soccer camp. Okay. But what we talked about last time is that even though we use the term random variable, it's not random in kind of chaos kind of sense, right? So even though the value for a variable is changing, there's still some rules associated with it in this value. And so again, think of your commute time. So your commute time, it doesn't randomly change between 3 seconds and 3 hours. It's always within a certain band. And in fact, there are certain values within that band that are more preferred than others. Okay? And so this kind of leads us to, a need to kind of describe these random variables in a particular way. Okay? Because, we recognize that, when we have random variables, the values can change every time that we measure it. But we want to see, what are some values that are preferred, and what are kind of the overall bounds of the So that's often what we want to know about random variables. What's the preferred value, and what are the limitations of how much it can. And so this is kind of the purpose of probability density, which we kind of just started talking about last. So probability density functions are a way for us to kind of describe the behavior of a random variable. So probability density functions, so oftentimes they're called PDFs. They're really kind of interesting. So, technically they are functions, and so you can have kind of the mathematical form for the PDF. But actually, the form of a PDF, or the way that people view them, the way that's actually most useful is the graphical form. So when you see probability density functions, you often see a figure or a curve rather than the mathematical function itself. Let me kind of show you an example. I'm going to show you kind of a it's one of the I would say kind of standard distributions, although it's not as common for use in engineering, but I think it's useful for kind of finding. So this is known as the beta distribution. And so it looks something like this. There's usually kind of a smaller end right here, and then at the other side, there's kind of a hump, just like So how do we interpret this probability density function? Okay. And so, for a function like this, you can see that we have a prominent peak. And so whenever you see peaks in a probability density function, this tells you that this is going to be the preferred value. Okay. Or if you kind of follow the peak down to the horizontal axis, okay, this right here is the preferred value. So the kind of the labels for these axes here on the horizontal axis, we have the random variable. I should say the value of the random variable. And then on the vertical axis, we have relative probability. Okay. And so wherever the peak is located, and usually for a lot of these probability density functions, they have a peak, at least one or two peaks. So those are the preferred values. So what that basically means that if you were to measure or if you were to observe this random variable, most likely you would get a value that's either at the peak or close to it. So I'd say that's kind of the first thing that you should kind of pay attention to when you're looking at probability density. Where's the peak, and what value does it have? Okay, but this probability density function is comprised of more than just a peak, right? So we have other parts of the function. And so on the one hand, you can see that this probability density function is, this one in particular, the beta distribution is bounded, right? And so there are regions or there are places where the probability density function reaches a value of 0. Okay. And so whenever the probability density function has a value of 0, that means our random variable has no chance of being measured at that point. And so the plot itself kind of gives you limitations in terms of what the value of the random. So outside the limits of this curve right here, a random variable. All right. So one last thing that I want to mention about this probability density function is kind of in between those. And so there will be regions like this region right here, where the PDF it's non-zero, and so there is a possibility for the random variable to take these values, but they're relatively low. Okay. And so these regions where you're kind of far away from the peak, but not quite at 0, we call these the tails of the distribution. I think the implication is that it actually looks like a tail of it. It doesn't really look like it to me, but mathematicians over here. The idea with the tails is that these are regions where technically it's possible for the random variable to take these values over near the tails, but the probability is very low. So possible, but low. All right, so that's kind of the basics of how to kind of interpret a probability density. So whenever you're talking about random variables, you're always going to see these. It may not be as smooth as this, and there's dozens and dozens of different distributions under the sun. But we'll focus, but for this class, kind of just for the short time that we have left this semester, we'll focus on kind of the most common ones, or I would say the most common one that's used in. Any questions on this so far? Okay. All right. So let's talk about how to interpret probability from a probability density. Okay, because oftentimes what we want to know is that if we're given a probability density function, and we have a certain interval, okay, we want to find out what's the exact probability that our random variable would be within that interval. So we often call this interval probability. And so we have a random function, a random variable x. Okay, we want to find out the probability that x is between two values, a and b. Okay, this here represents probability x is a and. So we took a look at this last time with the distribution function, but we can come up with a similar expression for probability density. Okay. And so for a probability density function, we're going to need to take the integral between a and b of that probability density. T right here. This is the probability density. So this is a little bit different than our distribution. Remember from our CDF, when we talked about CDFs on last Thursday, to compute a similar interval probability, we take the difference of the CDF. We just simply take the difference between the CDF of location B minus location A. But when you're talking about probability density functions, you actually have to take. We have kind of two tools right now. So we have the CDF, cumulative distribution function, and the PDF, the probability density function. And so I would say between the two, the PDFs are a lot more common, just because you have this kind of property where you can look at the peaks and say that those are probably the most likely values. The CDF is just a little bit more difficult. Same information from the CDF, but the PDF kind of does it in a more visual. Okay. We can also compute the mean and the variance from a probability density. And so the mean value for a PDF, we'll call that mu x is equal to the integral from minus infinity to infinity of t f of t. So this f of t is again the probability density function for a random variable. You're going to take that probability density function multiplied by t, integrate it. Okay. That's going to give you the mean value. So remember kind of our definition for the mean value. The mean value is just, you take a bunch of samples, you divide by the number of samples, that's going to be your mean for the value. Okay. Then we have a variance. So the variance of a PDF is a little bit more complicated. So I'm going to give it the symbol sigma x squared. So this is going to be integral from minus infinity to infinity of e minus mu squared, where this mu here is the mean. So before you compute the variance, you have to compute the mean. And so that's kind of the same as our definition from last time as well. And you multiply by the probability density F of All right, so next I have an example of how to compute these for relatively simple. Okay, so before I get into that example, are there any questions on this? Okay, so let's do an example to kind of see how these formulas are. Okay, and so to do that, I'm going to introduce another distribution. So this is another common one. It's not the one we're going to be using most often, but this one is just used a lot in general. So this is called a uniform distribution. And so the idea with the uniform distribution is that you have an upper bound and you have a lower bound. Okay? And then in between those upper and lower bounds, your random variable can take any value between those bounds, and the probability is equal for all of those values. Okay? And so it looks like a uniform function. So if we sketch out its PDF on the horizontal axis we'll have t, vertical axis we'll have f of t PDF. Okay. We're going to have a lower bound A, upper bound B, and then we have kind of a square wave that exists. Okay. And so what this tells us is that our random variable can take any value between A and B with equal probability. Okay. So the uniform distribution is interesting because there's no preferred value here, because it can really be anything between A and B. Okay. And so if you have a uniform distribution and it's between 8 and 12 or something like that, then you can take any value between 8.7, 9.4, 10.2, 7.7. Okay. All of those values you can take, and which value it takes is just kind of completely random. But I'm bringing this one up because the PDF actually has a very simple form. You can see that it's a constant value. Okay, so integration will be very easy. And so for a uniform distribution, our f of t is given by 1 divided by e minus. Where both b and a are constant values, and so this f of t is going to be constant. And so what we want to do for this uniform distribution is we want to compute the mean and variance of this mean. All right, so we're going to basically just apply our equation, our two equations that we went over to write the formula. Okay, any questions on just the setup for this problem? Okay, all right, so let's go ahead and get to it. So our mean, let's start with the mean. Integral from minus infinity to infinity of t f of t dt. So let's go ahead and plug in our f of t for this problem. We have a unique circumstance though. So normally we can see that our integration here goes from minus infinity to infinity. Okay. But if we look at our probability density function here, right? Outside of A and B, right? And so we look at all values less than A and all values greater than B, right? Our probability density function is equal to 0. Okay? We can do the same kind of trick that we use for Fourier. Right? So, instead of integrating from minus infinity to infinity, we can break up this integral. So we have integral infinity to A, C, T, plus integral from A to B, T f of T, plus integral B to infinity T f of T. Okay. Remember, you can always add successive integrals together. So what we've basically done here is we've kind of broken up the integration domain. And so you can see that together, when you add up these three integrals, we make up the same integration domain. So we need to integrate from minus infinity to infinity, but we've broken it up in a way that's going to be more. So this first integral here goes from minus infinity to A. The second integral starts at A, okay, so they kind of start and end in place. Whereas the second integral ends at B, the third integral starts at B. Okay? So you can always break up integrals like this, and so you can always break it up so that overall, as long as your integral is going to start or end and start at the same places, you can break up any. But this is useful for us, this form. Because in this region and this region, in these regions, we know that our probability density function has a value of 0. And so what we can do from there is that, if our f of t is 0, then we're basically just integrating 0. Right? We can just cross these. And so all we're left with is just an integral from A to B of t times f of t. Well, we know the value for f of t, so f of t is 1 over b minus a. Okay. Let's go ahead and perform this integration. And so for this problem, since we are integrating over t, so t is our integration variable, that's given to us by anything that's not t, we can go ahead and factor that out. Okay, so 1 over b minus a, that's just a constant. So let's have 1 over b minus a, integral from a to b. Okay. Whenever you're performing integrals, and this goes for Fourier as well, so I saw this a lot when I was grading from 5. You need to know what your integration variable is. And so whatever your integration variable is, you can't just factor that out of the integral. So what I saw a lot in homework 5 was that, that we're doing an integral for t. It was like t times sine of t or something like that. And people were doing that, oh, I'm going to take this t and bring it outside. So, and so you kind of, that kind of gave you the wrong answer for. So make sure you kind of pay attention to what the integration variable is, and you keep those variables within the. Okay. All right, so let's go ahead and integrate t. And so the integral of t here is fairly simple. So we have t squared over 2. Okay. And we're going to evaluate this from a to b. And so if we write this out, we have 1 over b minus a times b squared minus a squared all over 2. So technically, we're done here, and so that's the integral that's evaluated. But we can simplify this a little bit. So we know that b squared minus a squared. If we factor this out, this is equal to b plus a times b minus a. Okay. And so we on top we have b plus a, b minus a, all divided by 2 times b minus a. We have a b minus a up top, a b minus a on the bottom, and so we go ahead and cancel those out. So our mean is b plus a divided by 2. So our mean value, our average, is just simply just the average between the two bounds, right? So it's right kind of in the middle of A. Say B, you add A, by the way. So this makes sense, right? And so if we look at our distribution of probability density function here, you remember our random variable can take any value A and B, and it does so equally, right? And so if we were to sample, right? If we were to sample things, it would be kind of all over the place between kind of a random kind of thing. And so we took the mean, right? So we sampled maybe, let's say 100 points. We sampled 100 random variables. We computed this mean. Right? The mean should be right in the middle between those. And that's exactly what we got for our mean value for the uniform. So our answer should make sense. Any questions on the mean? All right, so let's go ahead and compute the variances. All right, so our variance, our formula for this is integral from minus infinity to infinity of t minus mu squared times t. Okay. That's just our formula for the variance. And so we can go ahead and plug this in and plug in for this. So there are quite a few things you can plug in for. So first of all, we can plug in for the mean, just solve for it. And we can also plug in for f of t, and we can adjust the bounds as well. Okay. So let me do that first. So our bounds are going to be from a to b. Okay. We're going to plug in t minus the mean, b plus a divided by 2 squared times f of t, which is 1 over b minus a. Okay. Let's go ahead and simplify this. Let's take our f of t, which is just a constant. Let's go ahead and bring this out in front. So we have 1 over b minus a integral b of t minus b plus a divided by 2 squared dt. Okay. All right, so you can do this integral in lots of different ways. So one way that you can do it, you can actually FOIL it out and integrate that. But this is a very kind of classical example where we can do U substitution. And so if we let U is equal to T minus B plus A divided by 2. Remember, B plus A divided by 2 is just a constant. So when we take the derivative of this, U, you just end up with E. All right, so that simplifies our integral quite a bit. So if we plug in this U substitution, what we get is integral from A to B of U squared du. Okay. I know this isn't the full U substitution, but we didn't change the bounds, but it's kind of how I did it. Okay. And so let's go ahead and integrate U. So this is fairly simple. And so we're going to have a 1/3 U cubed. 1 over B minus A. U cubed divided by 3. Okay. Let's go ahead and plug back in for U. And so we plug back in for U. What we get is 1 over 3 B minus A times T minus B plus A divided by 2 cubed, evaluated from A to B. All right. So now that we perform the integral, the last step here, well, it's going to be the most work, but the last step here is to plug into the bounds and then simplify. Okay. Okay. Let's go ahead and do that. So we have 1 over 3 B minus A times B minus B plus A divided by 2 Q minus A minus B plus A divided by 2 Q. Okay. So if we simplify this, we get 1 over 3 A. Inside this first parentheses, we have a B minus B over 2. So that's going to give us a positive B over 2 minus an A over 2. B minus A divided by 2 Q minus. And then for the other one, we have the opposite. So we have A minus B divided by 2. So I'm not going to show you all the steps here just because it's a little bit tedious, but the way that you kind of finish this out is you kind of FOIL this out. You do the B minus A cubed and you FOIL out the A minus B cubed. Okay. You simplify those terms. A bunch of terms are going to cancel out. Okay. And then once you can simplify that, then you end up with the form. After lots of algebra. Algebra, we get the following. We get sigma squared is equal to 1 over 12. E minus 3. Okay. And so if you want to see all the steps, they're in the lecture notes, and so you can definitely go and check that out. But but I did want to make sure we get the confidence interval. All right, any questions on this? All right, and so for the cases where you have kind of the functional form or the probability density function, actually, it actually is quite rare. But when you are given the functional form for the PDF, you can use these formulas to compute the mean and okay. All right, so let's go ahead and move on. And so let's go and move on to kind of the star of the show for this lecture and the next lecture, which is known as the normal distribution. It's also known as the Gaussian distribution. It's also known as the bell curve. So it goes by a lot of names, but the name I kind of hear most often is called the normal. A Gaussian distribution. So I remember when I first got into college, I was kind of introduced to this concept of a bell curve. So I never heard about it before, but then basically everyone's saying that the bell curve, because that's how every professor grades here. I don't know if that's still the case. I think we kind of moved away from the bell curve, or at least together. But maybe there's still but the reason it's called the bell curve is that if you actually plot out the probability density function, it looks like a bell. So let's look at the PDF of the normal distribution. And so it looks like the following. Just like that. So PDFs are really, really great tools because it's very easy to kind of interpret and it fits. I would say it fits a lot of what we think of like conservative. And so the first thing you'll notice is that there is a very defined word value. Okay. So we have a peak here. And then in the case for a normal distribution, have kind of equal variance on both sides, the peak or the location of the peak is exactly the same as that. Maybe I should do this. Peak. This is peak. Just wherever the peak is on the horizontal axis, this is the mean value. And so the thing with Gaussian distribution, with normal distribution, is that there's a very clear kind of preferred value, and it's usually very easy to spot wherever the peak is. Okay. The other interesting thing about the Gaussian or the normal distribution is that it has equal variance on both sides. And so I didn't draw it well because I'm an engineering professor, not an art. But if I were to draw this better, then what you should see is that on either side of the peak, it looks basically the same. So it basically looks like an even function around that peak. And in fact, you'll see the Gaussian come in lots of different flavors. So you'll see cases where you have a fairly small variance, and so that's given by kind of a very narrow peak. Or you may have a case with a very large variance, you have very wide. Let me kind of draw you kind of those two. So for cases with small variance. Small variance basically means that we know the value for this random variable with a lot more certainty. There's a lot less, random variation in its value. Okay. we may get a normal distribution that looks like this. Okay. You can see our peak is very narrow, and so basically most of the values that you're going to sample are going to be right around that peak. Okay. Or you can have cases with large variance where our peak is the height of the peak is smaller, but then the entire hill is one. Where there's a much wider range of values that this random variable take, but there's still kind of a preferred value. Okay, so the Gaussian or the normal distribution from lots of different flavors, depending on what the value for the mean is and what the variance is. Okay. So normal distributions like this or normal random variables are really, really nice models for random variables because in a lot of cases they kind of model exactly what we think about for random. Because the thing with the normal random variable is that, very clearly we have a preferred value. Okay? So there's going to be a mean for the random variable. But then we also have kind of equal variations on both sides of that preferred value. And a lot of times, when we think about uncertainty or uncertainty in engineering, that this is kind of the model, or this is kind of the what we think about for the random variable, even if we don't kind of explicitly kind of think about it. I'll just give you a very, very quick example that you've probably seen in your previous engineering class before. And so let's think about measurement uncertainty. So let's say that you're using you're using a ruler to measure something. Okay? And so when you measure something with a ruler, you have the preferred value, so you have just whatever you read off the ruler. Okay. And so let's say that you're measuring the width of this computer screen right here. And so let's say that we measure something to be something like 20 inches. Okay. But we know that whenever we measure something, there's always some uncertainty because when you're looking at a ruler, the amount of precision that you have is given by just how many tick marks that they have. Right? So maybe that the length of your computer monitor is 20 inches, plus or minus maybe 0.1 inches. And so the 0.1 inches, the way I got this is that maybe the tick marks on our ruler are not don't go down below 0.1. And so what we can say is that we can say that the size of our monitor is 20 inches, plus or minus the precision of our measuring. Right. So hopefully this is a concept that you're kind of familiar with in terms of measurement. We can take this, and we can fit it to a normal distribution. So what we can say is that we can make a normal distribution that represents our measurement of our computer screen. Where the peak is going to be where the amount that we actually measure. So this is going to be 20 inches. And then the variance over kind of the exact, we'll kind of go over a more precise definition of how the variance affects the width. It's not actually the width of the, it does affect it, but it's not, I'm not going to draw it all the way. But the width of this, of the peak here is given by a division. Right, and so you'll see me use the normal distribution for a lot of the random variables we're going to use from now on, just because it has this kind of very nice kind of definition. Kind of the properties of the normal distribution fit very well with kind of how we understand uncertainty. Okay. Any questions on this? Okay. So let me give you the functional form for the PDF. We're not actually going to use it just because this function is kind of a mess in case you're curious. And so if you end up doing kind of more work in probability statistics, you'll find that there's a lot of how should I say, a lot of very annoying stuff. The math isn't particularly very difficult to understand. It's just the function just are a mess. Okay. Okay, so our probability density function, so it can be f of t is equal to 1 divided by sigma times square root of 2 pi times e. And this e is going to be raised to the minus 1/2 power times e minus mu divided by sigma. You can see the function is a mess, and actually it's defined relative to the mean and defined relative to the variance as well, or technically the standard deviation. Signal with that. So we're not going to do anything with this. We're not going to integrate this or anything. In fact, because it's e squared, it's actually impossible to integrate by hand. But in case you're curious, if you wanted to plot this in Excel or you want to plot this in MATLAB, this will give you that. We also have the CDF. Again, this is just for your curiosity. This is capital F of t, and this is equal to 1 divided by sigma squared pi. And what you see is that this is actually we don't actually have the functional form for the integral is actually impossible. We have the integral from minus infinity t of e to the minus 1/2. Let me give a dummy variable here. So let me call this x, this mu divided by sigma squared. We don't even have a closed form expression for the CDF, just because when you try to integrate e squared, e to the something squared, that's impossible to do without numeric. Kind of funny. Okay. So the last thing I want to go over before we do confidence interval is this idea of the standard deviation. Okay. So I brought up the standard deviation very briefly last Thursday. Remember, the standard deviation is just the square root of the variance. But when you talk about the standard deviation of a normal distribution, it kind of takes on a new mean. And this is how, and I don't know, and maybe other departments still do this, but this is how, college grading systems in like the 90s and 2000s were. Okay. So remember, one of the most defining characteristics of the normal distribution is that we have equal variance on both sides of the mean, right? So we're equally likely to be kind of over the mean, and we're equally likely to be less from the mean. And that probably is given by the variance. Okay, so we have kind of an equal variance on both sides. The standard deviation, remember, is just the square root of the variance. Okay, so for standard deviation, we usually give it a symbol, just sigma, equal to square root of the variance. All right. And so for normal distribution, we use the standard deviation, or the standard deviation is useful for quantifying, how unlikely we are to deviate from the mean. Right. And so the numbers for this is that if you're one standard deviation away from the mean, you have a 68% chance of being within one standard deviation of the mean. In other words, the probability of mu minus sigma is less than t is less than mu plus sigma. Okay. So the probability that we're within this interval, okay, of the mean minus sigma and the mean plus sigma at the point, this is about 68%. Okay. It's actually a decimal, so it's actually 68.2347, something like that. We can just round to 68%. If you're talking about two standard deviations from the mean, then you have up to 95. So 95.5%. Probability u minus 2 sigma less than t less than mu plus 2 sigma is about equal to 95. Okay. So a lot of my college courses were kind of graded based on this principle. Okay. And so what a lot of my old professors used to do is that, you know, after you take an exam or something, you find the mean, you take the mean of the average score, give that score a C plus usually, and then depending on where you were relative to that mean, you would assign A. And so they use the bell curve to say that, you know, only the top 10% of the class would get A's, you know, the middle 40% would get like B's, the bottom so and such would get, you know, C's and D's and so on. And so it became kind of a very competitive thing. I'm hoping that other professors here don't do that. I remember there were like crazy things that would happen there. You know, this didn't happen to me, it's happened to one of my friends. So, this was in a class that was very competitive. And so this girl went up to my friend and she was like, oh, you know, I'll turn in your homework for you. And so I'm like, oh, great, thanks. And so this person took the homework and then just threw it in the trash so that, you know, when the professor wouldn't get it, he would get a 0 on the assignment. So, damn, the hell. So, you know, hopefully things aren't like that anymore. Usually engineering is more chill, but usually we're more we have more camaraderie than that. This isn't a pre-med class, but things can get kind of messy. All right, any questions on this? Okay, all right. So the last thing I want to go over today is this idea of confidence intervals. Right. So the idea with confidence intervals is that, you know, a lot of times, you know, we're not given the probability density function for a random variable. Right? So the probability density function it's a useful tool for kind of visualizing kind of in a perfect case when we know everything about a random variable. But a lot of times we don't have access to that. So the PDF is kind of like the most ideal case, right? And so if you have a random variable whose value is changing every time you measure it, whether it be due to uncertainty or whether it be due to kind of just random events, okay? The most ideal case is that if you have a PDF, because that PDF is going to give you basically all the information about the random variable. Okay? But most cases we don't have access to this, okay? Just because our events are kind of truly random and, you know, hard. So if you were to ask me, you know, is it possible for me to develop a PDF my commute times? Okay. Maybe if I measured my commute time over the course of like 3 years, then, you know, maybe I would have enough data to give you that, but oftentimes we don't have that. Okay. And so what we're doing most of the time is that we're relying on a finite number of samples or finite number of measurements to basically determine the properties of a random variable. All right, so for example, so let's say that you're performing a test, let's say that you're in 306A, 306B, and you're performing an experiment, right? Any good experiment, you're going to do it more than once, right? You're not just going to do the experiment once and say that's the result. You're going to do it more than once, and then you're going to use all those different results to obtain your conclusion. Right? And so, for example, let's say that you're doing a bunch of tests and you want to compute the average or mean. When you compute the mean in this sense, we usually call it the sample mean. And so this is a formula we know before. So the sample mean is just simply 1 over big N, where big N here is the number of samples. And you take the summation of I is equal to 1 to N of each measure. Okay. And the same thing for the variance. So we can also have the sample variance. So the sample variance, sigma squared is equal to 1 over minus 1 summation I is equal to 1 N of xi x bar. All right. So if you have a if you have a finite set of measurements, you have a finite set of samples, this is how you compute the mean and the variance. Okay. One important distinction that I want to make about these formulas here is that these are not formulas for the true mean or the true variance. Okay? These are only estimations based on the data that we have available. Okay. If you wanted to know what the true mean of a random variable is or the true variance, you would need the PDF, right? And so if you have the PDF, you could plug into those integral formulas that we talked about earlier today, okay? And that would give you a measure for the true mean and the true variance. Okay? But when you compute the mean in this way, using this summation formula, and you compute the variance in the same way, it's important to kind of remember that this is not really the true mean. Oftentimes you're going to get close, right? And so it's not like you're going to have big differences in most cases. But it's important to kind of remember that this is not kind of the true rule. Okay. And so of course, the expectation is that even though these are not values, these are not expressions of the true mean and true variance, the expectation is that the more measurements that you actually take, so the more experiments that you run, the more times you actually measure it, you're going to get closer and closer and closer to the true mean and true variance. And so if you were to do, 3 tests, okay, and compute the mean that way, that's not going to be as valid, that's not going to be as, I should say, as trustworthy, or you're not going to be as confident in that as if you did 30 tests. So this is kind of something that, I think a lot of people just kind of understand just this, so the more measurements that you take, the more, the more tests that you run, you're going to have a much more reliable answer. Okay? But then that kind of begs the question of, how much is enough, right? And so, if we wanted to estimate the mean of a certain measurement or certain value, how many tests would we need to run before we actually get something that's wrong? So this is an important question to ask, whenever you're doing any kind of engineering experiment, right? Because whenever you're doing an engineering experiment, a lot of times, if you're working for a company, this usually involves developing a test case and running the experiment, which usually takes a lot of time. It takes a lot of personnel. Okay? A lot of times, you want to know beforehand, if we're going to do this experiment, how many times do we need to run it before we actually are really confident in it? Because sometimes, there are going to be some tests, let's say that you work in the aerospace industry, right? And so you want to test kind of the effectiveness of a new wing design. Right? So let's say that you're redesigning a wing on an airplane or rocket ship. Sometimes it just may not be feasible for you to really get enough measurement. Usually, if you're testing a new wing, then you have to build an entire aircraft, right? And so how many aircrafts and how many tests you have to run on that aircraft before you get something reliable, if that number is something in like the hundreds or something like that, then that may not be feasible. Okay? And so this is often something you want to know beforehand before you kind of commit to running a lot of experiments or to running a lot of tests. Okay? And confidence interval is going to give us a way to. Okay. All right, so let's go ahead and define confidence. And so the confidence interval of an unknown parameter is the interval that describes the some level of certainty, the value of that unknown parameter. That's what we're assuming. Let me define like this. So the confidence interval is kind of two things. So on the one hand, it is an interval. So it's kind of a lower bound and an upper bound. Okay? But associated with that, you also have a certain level of confidence, usually given as a percentage of how confident you are that the value is going to be within that. And we actually use confidence. So I would make the argument that we actually use confidence intervals fairly naturally, kind of in our everydays. For example, let me bring up my commute time because it's probably the worst part of my day. It's driving to school. Right? The 60 freeway and the 57 are just always so awful. Right? And so let's say that I can say with 95% confidence. I can say with 95% confidence, my commute time will be between 45 and 55 minutes. And that's not in my notes. That's how I feel today. That's how I feel kind of currently where I live. Okay. And so if I'm gonna drive to school on a Tuesday, Thursday, then it's gonna be between 45 and 55 minutes, 95% confident. Okay, and so on next Tuesday, because remember Thursday is our midterm, next Tuesday, we'll talk about how we actually quantify this and how we actually compute this for just a given random number. Okay. All right, so thank you guys for coming today. I know it's kind of the day before the midterm, so I appreciate you guys coming out. Remember Thursday is our midterm, so please show up in person for that. There's no plan to offer the exam virtually. And so remember, you can bring your writing utensil, you can bring a cheat sheet, and your calculator. Okay. So I estimate that you're going to need all three of those, but you will have all three of them. If you have any other questions leading up to the exam, I'm always available through email, office hours, or better appointment. Okay. So best of luck studying, everyone, and I will see you all on Thursday. No, so they're decimal values. Yes. Yeah. So it's not strictly the problem. You can't read off the probability. So it's a little bit more kind of like we said, there's infinite possibility. So in order to actually get and the PDF is more of a vision. So you that there's relatively versus like a normal distribution of not that. So there's relatively more than like more family. Yeah. Like 1/1 is right. I don't know. Does it get you a value? Right. So yeah. So don't read into the actual values too carefully. If let's say if you go from 0 to 1, right? The value for 0.1 is 1, but then the value for 0.7 would also be 1. So relative to 0.1, it has the same relative. Yeah. Mitchell, any final questions before I wrap it up? Okay, all right. I will see you on Thursday.